Hello, I'm Ha Rim Jeong. Let me start my midterm oral presentation of Fourier optics. There are 5 chapters. At first, I will explain what Fresnel diffraction is, and then I will show you how to simulate Fresnel diffraction with MATLAB. And similarly, I will explain Fraunhofer diffraction and show you how to simulate Fraunhofer diffraction. At last, there are some references. We can obtain Fresnel diffraction integral by simplifying Huygens-Fresnel principle with binomial expansion for R01. Of course, there are assumptions to binomial expansion, like G is much larger than x minus Cauchy and y minus eta. And then we can get this Fresnel diffraction integral that u Cauchy eta is amplitude of electromagnetic wave in the aperture plane, whether u xy is amplitude of a wave in the image plane. So if we know all the information of aperture plane, we can calculate the amplitude of wave in the image plane. Fresnel diffraction integral is seen to be a convolution of u Cauchy eta and h, where h is this. By convolution theorem, the Fourier transformation of convolution between u and h is product between Fourier transformation of each u and h. So by inverse Fourier transformation of this, we can figure out what uxy is. Fresnel diffraction integral can be expressed a little bit different way in equation 14. Expansion of x minus Cauchy square and y minus eta square, and then exponential x square plus y square term can get out of integral, because integration is for Cauchy and eta. Finally, we can get this for 17 equation, which is another form of Fresnel diffraction integral. This equation is Fourier transform of u Cauchy eta product exponential term. So by Fourier transformation of u Cauchy eta product exponential term, we can figure out what uxy, which represents the amplitude of wave in the image plane. Fresnel diffraction by a square aperture can explain classical approach based on the convolution representation. From equation 14, if we consider a square aperture of 2w width, the convolution form can be replaced with the product of two I functions. By changing variable with alpha and beta, and then iy can be calculated by using Fresnel integral. And there is Fresnel number that represents by width square over lambda z. The Fresnel number represents the type of diffraction. If Fresnel number is bigger than 1, that diffraction could be Fresnel diffraction, and if Fresnel number is smaller than 1, that diffraction could be Fraunhofer diffraction. This is classical approach of Fresnel diffraction integral. Now here are MATLAB code for Fresnel diffraction. I used convolution method to calculate Fresnel diffraction integral, and this is it. First part is setting variables, and second part is making xy plane for calculation, and third part is making square aperture, and last part is calculation of convolution by using convolution theorem with Fourier transformation. To find out uxy, product Fourier transformation of aperture u1 and Fourier transformation of convolution corner h, and then inverse Fourier transformation of the result of the product, we can find out uxy, because uxy is convolution of small u and small h. This is Fresnel diffraction for square aperture. The first one is case of small Fresnel number to large Fresnel number, which we can see changing Fraunhofer diffraction to Fresnel diffraction. And second one is for large Fresnel number, which represent Fresnel diffraction. Start with Fraunhofer diffraction is now changing to Fresnel diffraction as NF is rising. And this is for large Fresnel number. This is Fresnel diffraction of square donut aperture. You can see large diffraction pattern near the edge. Chapter 3 is Fraunhofer diffraction. Fraunhofer diffraction is come from one of Fresnel integral. Equation 417 is Fresnel integral. If G is much larger than K dot cushy square plus eta square over 2, then quadratic phase factor goes 1, and then Fresnel integral becomes this. This is Fraunhofer diffraction. Fraunhofer diffraction is proportional to Fourier transformation of u cushy eta. So we can calculate diffraction pattern by using Fourier transformation easily. This is MATLAB code for Fraunhofer diffraction simulation. First part is getting image of aperture. I use a snowflake image for the aperture. Second and third parts are also making aperture that combines several apertures. And last part is calculation of Fraunhofer diffraction by 2D Fourier transformation of aperture. This is Fraunhofer diffraction of moving snowflake. When I made this diffraction, at first I expected diffraction pattern to be dynamic, but it didn't. And then I realized that one snowflake has own diffraction pattern, and The number of same aperture does not affect diffraction patterns. Moving snowflakes does not change much. So I changed the scale of snowflakes aperture, and this shows one snowflake has one diffraction pattern, and the smaller aperture makes big diffraction patterns. I vary scales of snowflakes aperture 1000 to 10,000. Let's see. The bigger the aperture, the smaller the diffraction pattern. This is diffraction pattern of moving several scales aperture. At 3 seconds, we can see the diffraction pattern of one scale aperture. And diffraction pattern of last part of movie looks like one scale aperture diffraction pattern. I referred to Introduction to Fourier Optics, Internet, MATLAB help, and lecture note or PPT of Fourier Optics. Thank you for watching.